Hello everyone. In this session, we'll talk about the numerical integration, which is actually the approximation of areas using some different numerical integration techniques. So let's right away start with a simple example. Let's suppose we are given a function fx is equal to x square plus 1. And we know that this is a parabola since it is an x square and the leading coefficient is positive. So this is a parabola which is opening upward. So let's just draw a rough sketch of this parabola. So over here we have the coordinate axis. This is the vertex, which is 0, 1, and the parabola goes something like this. This is 0, 1. Now, suppose we are interested in finding its area between 0 and 2. This is 2 over here. This is 0, of course. So we need to find the area between 0 and 2. So what will we do? We'll integrate fx with respect to dx within the limits 0 and 2, which will actually give us the area of the shaded region. This is not an approximation, of course. So the area is exact, and this comes out as we write x square plus 1 times dx. Then we integrate between 0 and 2. Integral of x square is x cube over 3, and integral of 1 is just x. We put the limits from 0 to 2. After putting the limits, this comes out as 14 over 3, which is approximately 4.67. So this is the exact value of the area. Now let's talk about approximations. In approximations, what we do is, let's first of all draw the same curve once again. I will draw a little bit wider this time. So let's suppose this is the curve, and over here we have 2. We need to find the area between 0 and 2. Objective is same. Now, in order to approximate, what we do is we divide the region, which is we divide the area of interest or the region of interest in various rectangles. What this means is the rectangle will behave or will look something like this. Now, how these rectangles are made, what is the width, what is the height, that we are just gonna discuss now after this. So that is how the rectangles will look like, an approximate figure. Obviously, this rectangle will have some breadth or width, it will be delta x. And the height of any rectangle, let's suppose over here, if you talk about this rectangle, so its height is actually the functional value at that particular point of x, given that this figure is y is equal to fx. So height is fx, and the width of every rectangle we keep same, which is delta x. Now, since we are approximating using the rectangles, then the approximation will be the sum of the areas of all the rectangles. Let's talk about any one rectangle over here. So this is any one rectangle. This is an enlarged version of the rectangle. So width is already delta x, we already know. Height is f of x. So what do you think the area of this rectangle would be? Area is length times width. So area of one such rectangle will be delta x times fx. But we are not just interested in one rectangle. We have to find the sum of the areas of all the rectangles. So total area comes out as, we put a sigma over here. What the sigma means is, I will just let you know in a minute. We write delta x times fxi, where the value of I ranges from 1 to n. So this is the formula for the total area. Now, what sigma means is that is actually a summation of all such values of rectangles, of the height of the rectangles. What fxi means is, it is the width of the rectangles which are starting from 1 and ending to n. So if we'll expand this formula, this gives us, since delta x is a constant, it is not dependent on I, we can take it outside, and on over here we'll get fx1 plus fx2 plus fx and so on. We have to add all these terms and multiply by delta x to get the value of area. All right, now another last formula is what is the value of delta x? So the value of delta x is b minus a over n, where b in our case is the last point where we have to find the area. So b in our case is 2 and a in our case is 0. So just like this, we have to place the value of b and a, and n is the number of rectangles which we are forming inside the region. Uh, will in a couple of minutes we'll also come to know that more are the rectangles and more accurate, or more nearer our approximation is to the exact value. All right, let's start now with the technical some different ways to approximate the numerical integration. So let's talk about something which is called Riemann's sum. Now, Riemann sum is actually of three kinds. The first kind is called left hand points. All these three are based on making rectangles inside a region. All right. So the graph, of course, remains the same. Y is equal to x square plus 1. These are the coordinate axes. Over here we have 2. This is 0. Now, what we have to do in left hand points is we make a straight line. We mark A, which in our case is 0. We mark B, which in our case is 2. Now we find the value of delta x first of all. So delta x, we know that it is B minus A over n. What is B? It's 0. A is, the B is 2, A is 0 over n. Let's suppose we are as of now interested in making 4 rectangles. So n will be 4. So the delta x comes out as 1 over 2. Now we place various points on this number line with increasing delta x. So 0 plus 1 over 2 is 1 over 2. 1 over 2 plus 1 over 2 is 1. 1 plus 1 over 2 is 3 over 2. And there we have already 2. Like this, we place the values. Now, left hand point means we start from the leftmost side and take 4 points. In order to take 4 rectangles, although we have to take a total of 5 points, but for calculation point of view, we'll just take the first 4 points starting from the left. So from the left, we have this is 1, this is 2, this is 3, this is 4. These are the 4 points with which we are interested to find the area as far as the left hand point Riemann sum is concerned. Now, how does the area look like? Area will be delta x times f of x naught or x0 plus fx1 plus fx2 plus fx3. That's how the area looks like. So delta x is just 1 over 2. Fx naught is f of 0, then f of 1 over 2, then f of 1, then f of 3 over 2. This is the value, approximate value of the area. So let's simplify this further. How are we going to find all this? We know the value of fx as 1 plus x square. So for f of 0, we place 0 instead of x, so we get 1. For f of 1 over 2, we place 1 over 2 instead of x. So likewise, we are placing all the values, and this is what we get. This is just a calculation part. So the approximate value of the area which we get in this case is 3.75. Okay, one thing which is worth noticing is, what was the exact area? It was around 4.67, and this area is 3.65. This means that in our case, this is an under approximation. Why it's an under approximation? Because the approximation which we got is less than the actual value. Okay, let's visualize that what is actually happening over here. So the graph will help us to visualize. Let's first plot our points. So this is 1 over 2 here. This is 1 and this is 3 over 2. Absolutely fine. So let's write these terms as well. All right. So for the left hand point, what we do is we mark the values of the functional points at the curve. So this is where f0 is. This is where f of 1 over 2 is. This is where f of 1 is, and this is f of 3 over 2. We are not as of now interested in x equal to 2. In order to make rectangles, start from the left, go towards the right with a straight line, come to the next point and then come down. This is the first rectangle. Likewise, start from 1 over 2, go over to the right, stop at 1, go down. Another rectangle, start from, let's just redraw this. They're supposed to be at the same point. So yes, this is a little bit better. The next one will be likewise same, and the last one will also be same. So these are the four rectangles in which we are interested, and and the area which we just found is of these four rectangles only. Now, it makes it pretty clear that why this is actually an under approximation, because we clearly see that the rectangles are below the curve and there is some gap over here which we have not considered in our areas, right? So that gap is missing. That's why this is an under approximation, and this is the visualization of the left-hand points Riemann sum. All right. Another piece of information is usually the left-hand point is denoted by L followed with a subscript of the number of rectangles, which in our case is 4. So if a question says that find an L4 of this particular function, it means that you have to use the left-hand approximation with 4 rectangles to find the areas. So this is the notation for the left-hand point Riemann sum. Let's talk about the next one now. So next one is the right hand point approximation, which is also a Riemann's sum. Now this must be you must be able to figure out that what is this all about. The procedure is exactly same. What we do is we place a number line here, we mark A, we mark B. Delta X value we already know, we already calculated, it's 1 over 2. We plot our points, so this is 1 over 2, this is 1, this is 3 over 2. Now for the right hand point, the only difference is we also take 4 points, but starting from the right. So in this case, we'll start from 1 over 2, we'll leave 1, we'll leave 0 over here. So 1, 2, 3, 4. These are the 4 points of our area of interest, and the value of area in our case will be delta x times. Now we'll start from 1 over 2. So we have 1 over 2 plus 1 plus 3 over 2 plus 2. So this is the value of area. Let's substitute the values over here. So this is 1.25, this is 2. This is just the calculation part. And this value comes out as 5.75. Now you know that if I'm going to call it an over approximation, that is absolutely fine, because the actual area was 4.67 and this is more, and you must have also figured out by now that why is this an over approximation. This is an over approximation because the rectangles which are going to form will be above the graph. So let's try to visualize this once again. This is 2, this is already 0. All right. Now, the first things first, we plot the points here. So this is 1 over 2, this is 0, 0, of course, this is 1, and this is 3 over 2. Now we plot the functional points. So this is 0. In fact, we are not interested in 0. We start with 1 over 2. So this is 1 over 2, this is 1, this is 3 over 2, and this is 2. Now in this case, the only difference is the rectangle which we make is we start from these points and we go over to the left. So we start from this point, we go over to the left and drop here. This is one rectangle. We start from this point, we go over to the left and we drop here. We start from the right, this point, right side point, we go over to the left and drop, and likewise over here. So these are the 4 rectangles, and clearly we can see that the rectangles are above the curve. So the area which we are getting is more than the area which we are getting is below, is the rectangle are actually above the curve. This means that this part is actually extra in our calculation. That's why the area which we are getting is more than the actual area. And another, just like L4, this one is denoted by R4. This is the notation for the area using the right side Riemann sum with four rectangles. Let's talk the last one over here. So the last Riemann sum is midpoint. Riemann sum. So we talked about left, we talked about right. What is this midpoint? So procedure is same. We draw a number line, we plot A, we show B, we show our intermediate points. Now for midpoint, obviously as the name suggests, we are interested in midpoints. So one midpoint is here, second, third, fourth. We have four midpoints, and that's what we are interested in. Midpoints, let's name these midpoints as this will be 0.25, this will be 0.75. Over here we have 1.25, and over here we have 1.75. All right, so the formula is very similar. Area will be delta x times. Now we start from the midpoint. So we have f of 0.25 plus f of 0.75 plus f of 1.25 plus f of 1.75. Let's find all the values over here. So we have 1 over 2 times 1.0625 plus 1.5625 plus 2.5625 plus 4 this is 0.625. So this value comes out as 4.625. We see that this value is quite near to our exact value, which is 4.67. And let's visualize this midpoint, what is happening actually in the graph. Let's draw a curve over here. So this is the curve. This is a graph. I've intentionally drawn a wider curve to help us understand better. This is 0, this is 2. Now, first things first, we plot our points. So 1 over 2, this is 1. This will be 3 over 2. In fact, the 1. Okay, so for the sake, let's do one thing. Let's clear these points and make some gap so that we can better visualize this. If over here we have 1 over 2 and over here we have 1, this means that this is 0. This is, we are talking about the midpoints now. So this is 0.25, this is 0.5, this is 0.75, this is 0. Over here we have 0.75. So this is 0.75, this is 1.25, and this is 1.75. Procedure is same. We first plot or we first show the functional values. So one midpoint is here, one midpoint is here, another midpoint is here, and another midpoint is here. For the sake of simplicity, we also draw some parallel lines at the intervals. So one is this, one is this, one is at 1, one is at 3 over 2, and at 2 we have already drawn. Now, what we do is we draw a horizontal line such that it passes through the midpoint. So this is the horizontal line which is passing through the midpoint. 1, this is 2, this is, oops, so this is a better one, this is 3, and this is 4. All right, so what we do is we just drop them down. So this is 1, this is 2, this is 3, and this is 4. So these are the 4 rectangles which we have approximated now. You can clearly see that why is this more closer to our actual answer? Because if some part is more, then some part is also less. So in a way, it is getting compensated. That's why midpoint rule is actually more accurate than the left and the right side Riemann sum. And just like what we denoted earlier, midpoint is denoted by M. So in this case, M4, this is the notation for the midpoint. So what we learn from this is midpoint is actually more accurate, let's say, as far as the approximation is concerned. And another point which I would like to tell you is more are the rectangles. In fact, I will write it clearly that more are the rectangles, more closer is our approximation. So that is very evident because whenever you will take more rectangles, it will, it will be more crowded and the area tends to be somewhat more closer and closer and closer to the actual answer. All right. So let's move ahead and talk about another procedure of numerical integration now, which is called trapezoidal rule. Now, what does this trapezoidal rule means? In the first three, we were talking just about rectangles. So trapezoidal obviously means that we are now talking about the trapezoids. In trapezoidal rule, one different major difference is while in rectangle we took just the 4 points, whether they are the first four or the last four or the mid four, it doesn't matter. We took 4 points. In trapezoidal rule, we take 5 points. I mean, given that, of course, the example remains the same. We have x squared plus 1, and the approximation needs to be done between 0 and 2 using 4 rectangles. So this, using the 4 trapezoids in this case. So this remains the same. The only difference is even if we are talking about 4, now we have to take all the 5 points. First of all, let's write the formula. So let's represent trapezoidal rule will be represented by Tn. So that will be delta x over 2. We have fx naught plus 2 times fx1 plus 2 times fx2 plus 2 times and so on. And the last one will be, so second last will be f2 times f of x of n minus 1, and the last one will be without 2, so just f of xn. So this is the formula which we have. Delta x remains the same, and the number line will also remain the same. The only difference is we'll take 5 points now. So this is 0, this is 2, this is 1 over 2, this is 1, this is 3 over 2. So in this case, our formula becomes delta x is same, right? So delta x is 1 over 2 over 2. We have f of x, f of 0 plus 2 times f of 1 over 2 plus 2 times f of 1 plus 2 times f of 3 over 2 plus, and the last point is just f of 2. So this is how the trapezoidal approximation works. And if we are going to solve this, we'll get the approximate value as 4.75. So we can see that this is also a great value to approximate because the exact answer was 4.67 and we are getting 4.75, which is pretty close. But this is also a good piece of approximation. Let's try to visualize this as in what is actually happening in the graph. So we draw a curve over here. These are the coordinate axes. We are just interested in quadrant 1. So this is the area of interest from 0 to 2. Procedure remains the same. So we plot 1 over 2, we plot 1, we plot 3 over 2. And in this case, now we show the functional values at each of the 5 points. So 1, 2, 3, 4, 5. Now, in earlier 3 cases, we were making rectangles, but now we are interested in trapezoids. So in trapezoid, what we do is we join all these points. So first with second, second with third, third with fourth using a straight line, fourth with fifth, and then we drop a straight line down. So you can clearly see that we now have 4 trapezoids. If I will expand this over here, this is actually a figure like this. This is a trapezoid, right? Because we have 2 parallel sides and 2 non-parallel sides. So this is a trapezoid or a trapezium. So we have divided our area in 4 trapezium in this case using the 5 points, And clearly you can see that all these trapezoids somehow balances the area. Like over here, this is the under area which is taking, and here it has taken some extra area. So in this way, they balances the area among each other, and that's why the result is more accurate or more nearer to the accuracy as compared to the left and right side points. So this was all about the trapezoidal rule, along with its visualization. The last one which we are going to talk about in this session is Simpsons one-third rule. So we write Simpsons one-third rule. And just a piece of information that this is the most the accurate way to do a numerical integration, which is very close to the actual answer. Let's first start by writing its formula. It is different from the above four in various ways, which I will talk about in a couple of minutes. So the formula is, we have delta x over 2, sorry, the delta x over 3, because it's a one-third rule, so we have 1 over 3 over here. That's why it's called one-third. We start with fx naught. We write 4 times fx1. Then we write 2 times fx2. Then we write 4 times again. Then we write 2 times again. And so on, we continue till 4 to 4 to 4 to alternate. We end with 4. Sorry, the second last has to end with 4. That is very important. And the last one is without any coefficient. So this is what the formula looks like. Let us first calculate the area of our example, right? So the value of delta x was 1 over 2 over 3 we already have. Now fx naught is what? F0. Over here we have 4 times f of 0.5. Here we have 2 times f of 1. Here we have 4 times f of 1.5, and the last one is without any coefficient, which is just f of 2. So let's put the values again. I've already done this calculation. So surprisingly, this value comes out as 4.666666, which if we will approximate even to 4 decimal places, this will be 4.6667. This is the approximation till 4 decimal places. You can clearly see our answer was 4.67. That was our exact answer, and you can see how close these two are, right? So this is very accurate. Yes. Now I was talking about this differs with the above four in a couple of respects. So let's write those down. First thing is, this is applicable only when n is even. In our case, n was 4. That's why it was applicable. So this is one thing which we have to remember. Second thing is, this uses quadratic approximation. I'll talk about this in a minute. And the third one is, this is the most accurate. Okay, let's talk about its visualization, where I will talk about how it's using the quadratic approximations to make it more accurate. So let's draw a curve over here. And mind it, this is just for the understanding point of view. So this is 0, this is, over here we have 2. Now, before I move to the quadratic, let's see that how the others were getting approximated. They were linear. Why they were linear? Because if you talk about Simpsons, we join the 2 points using a straight line. Straight line means linear. If we talk about midpoint, we join the 2 points using a straight line, again linear. Left hand side or right hand side, all are linear. So all our 4 cases which we talked about were linear. But in this case, in Simpsons one-third rule, what we do is we approximate the region which is in between the 2 points using the quadratic approximation. So how this works, I'll just give you a brief idea about that. Let's first start by, again, we have to use the 5 points. So we'll plot the functional values at these points. Now, had it was Simpsons, I would have surely connected these two just like this, straight line. But sorry, had it was trapezoidal. But in Simpsons, In between these 2 points, let's suppose this point is x1, y1, and this point is x2, y2. Between x2, y2, we actually make a quadratic equation in terms of ax square plus bx plus c using these 2 points, and the curve which we get is actually made in between the points. So that is not actually a straight line, that is a curve. Likewise, we make over here, likewise, we make over here, likewise, we make over here. This is not the best way to represent, but I hope you get an idea. We drop the perpendiculars at our intervals, and this is the area which we get as per the above formula. So you can see that when it is linear, then obviously some region is left. But when it is quadratic, as in it is in a shape, it tends to follow the shape of the curve. And when it follows the shape of the curve, obviously it means that it is getting more and more closer to the actual answer. And this also clears up the fact that if we make the rectangles very much near, for example, I make 1, 2, 3, 4, 5, 6. I make 6 rectangles. So obviously this means that these points are very close. So whenever the points are very close, whatever approximation which we'll do, well, actually, the line whichever we are making, that will be actually very close to the functional graph or the functional curve. And whenever our approximation, the approximated lines tend to come very closer to the trajectory of the curve, this means that our approximation is getting very, very, very close to the actual answer. So this was about Simpson's rule. So just to sum it up, what we read in this lecture is we read about numerical integration techniques. We read 5 ways to approximate. The first one was, these three are for Simpsons. So these three are, I'm sorry, this is for Riemann's. So this is for Riemann's left side. We talked about Riemann's right side. We talked about Riemann's midpoint. We talked about trapezoidal, and of course the king of all, Simpsons. And we saw that this was actually somewhat an under approximation, and this was in our case usually, and also it's an over approximation. These three were the if you can say, the accurate among all these 5, with this being the most accurate, and these two are actually also very close to the exact answer. So this is the summary of our lecture today, and I hope this was helpful. So we'll end this lecture here, and I think I will see you soon.